Good morning, good afternoon, good evening. We're coming from the world to you, the world, with our weekly Quantum World Detangled today with Denise.
Hi, everyone. Denise Ruffner from Cambridge Quantum Computing, located in Los Angeles, still staying at home. So coming to you from my home office.
Hey everyone, Tommaso from Entropica, talking to you from Singapore. Likewise, also still at home. Now is evening, still calling you from my work office as well.
And André König, the CEO of Interference Advisors, still coming from Miami, but it's a gray and rainy early morning, so sitting at my kitchen table and excited to speak to you today. Denise, it's pretty early for you, right? No sunrise yet in California.
Yes, in order to accommodate our guest, I got up at 4:30 today. So
Whoa.
I know, but I kind of feel that it's my career. One of my career competencies is to get up at all times of the day and try to be competent. I wanted to talk to you this week. We just got news of two different companies getting funding, which is very exciting. The first one is Entropica Labs out of Singapore. So congratulations to Tommaso for getting $1.8 million in funding. Is that accurate?
Yes. It's actually in Singapore dollars, it's 2.6 mil. Thanks a lot. Really, the congratulations should go to the whole team. I'm really just the one who writes LinkedIn posts.
And then also last night we heard that Quantum Motion Technologies in the UK has just closed $8 million in a Series A investment. And they're another quantum computing company doing silicon spin technology. So just some investment activity, which I think is really great in this time of quarantine. A lot of people say that nothing's going on, and I think there are things going on, and it's up to us to keep on pushing. So,
and on my end, who is focused on the investment community, I can tell you there will be more investment announcements coming out in the next weeks from some of our fellow quantum entrepreneurs. So good companies and good teams are absolutely able to raise money.
Fantastic. There was fantastic work put on the archive this week. I just picked one paper that I'm going to very quickly share with you. It's not maybe what everyone else might be thinking, still a great one. This paper is called Faster Classical Boson Sampling by Clifford and Clifford, which is really interesting, actually. If you guys are not familiar with boson sampling, it's a technique that was developed quite a while ago now. Very interesting because while it is not necessarily a useful technique, it is a proposal that could be used to demonstrate that quantum computers are better than classical computers at solving certain problems, in this case, boson sampling. But what I really like about the quantum computing efforts is that classical computing always strikes back. And specifically in this paper, there was an improvement on the best known algorithm for boson sampling, and they managed to improve the performances, which makes it even more difficult for a quantum computer to challenge a classical computer on this problem specifically. So it's a great work of computer science, very interesting. I'm gonna stop sharing so we can go back to see each other. And it also shows how efforts in quantum computing are beneficial also for classical computing and for algorithmic development in general. So hopefully people will find it interesting. I certainly did.
It is interesting. I've made the point before that in quantum computing, we don't just compete for supremacy or advantage, but also against other technologies and innovation from the business point of view, because companies only have that much budget and innovation resources to spend. So this is interesting. Denise, what stood out to you this week?
Really just the fact that there's still investments going on and that there's still a lot of activity. I know we've had actually a number of sales leads as well this week. So things just keep on continuing, and I encourage everybody not to let the home confinement get you down and to just keep on doing business as usual, because people are still active and people are still very interested in talking to all of us.
Absolutely, and something that I see in my conversations with your colleagues every day as well. So we'll have to keep fighting. I don't have news this week. I have a guest, and we're very excited to have him. We are not going to have too many guests on our show, but every now and then we'll make an exception. I had an interesting conversation with one of his colleagues earlier this week, and he introduced me to a new concept that he called co-design, which is both, if I understand correctly, a technical but also business development concept on how to go to market with quantum computing solutions. And some bold claims were made as well what this can potentially deliver in the next few years. So excited to welcome the CEO and the co-founder of IQM. And Jan, if you wouldn't mind sharing your thoughts and perspective on what you're doing with co-design and how it might be different, interesting, and what it might be able to deliver.
Yeah, thanks, André and Denise, Tommaso, for giving me the opportunity to participate here. I think it's a great format. I'm dialing in from Helsinki. So yet another time zone. It's afternoon here. So yeah, we at IQM, we are following this co-design approach, and we are very happy to have Enrique on board since March, actually. He's leading our efforts in Munich. So IQM has the roots in Finland, here in Helsinki. This is where we are building the hardware for quantum computers. And really the idea of the co-design is that you do the hardware development together with the algorithmic work hand in hand, and in this way try to get the best out of the system. Because I think everyone agrees that at the moment the challenge is that the algorithms require more than the hardware can deliver for most of the useful cases. So there's a gap, and the question is, how can you close this gap? And our view here is that this gap can best be closed if both sides, so the hardware and the software, are working on the same problem. And in this way, you hopefully can reduce the overhead in qubit count, for example, to an extent that the quantum advantage can be reached soon enough to survive quantum winter, for example, what is the fear of many people out there, especially in the startup community.
Tell me a little bit about the funding environment. I think you've been very successful at raising funding, or I know you've been very successful at raising funding. And do you think that your unique approach is what's attracted investors, or can you say a little bit more about your success in raising funding?
Sure, I can. So when we were pitching for our seed round, we didn't actually have this concept yet in our toolbox. But there we were really pitching for the hardware effort. So if I explain a little bit more about the company, so what we are doing as IQM here in Helsinki is building superconducting quantum processors. So we are following the superconducting approach, and we have certain aspects in our processor design that allow us to speed up the operations for quantum computing, namely the reset of the qubits, then also for the gates and for the readout. We have developed novel concepts. And the idea here on the hardware level is to speed up, not only to maybe reach the end of the algorithm faster, but to fight the short lifetime that you have, especially in superconducting circuits. So this is the main idea, and this was the let's say key innovation for the pitch of our seed funding. And it was very successful, as you mentioned. It was around $12 million earlier. And we have been using this money so far, I think, very efficiently, growing a team. But this co-design concept really came then together with Kike and his great ideas. So this is now a little bit of change in the strategy that we have been following over the last year.
So actually, I have a question about the co-design thing. Is very interesting. Does it also mean, and this is just for me to understand, does it also mean that the design of the chip. For example, the physical position of the artificial atoms depends on the algorithm that you're developing?
Yeah, this is one aspect. So the co-design actually has, let's say, different levels of how far you can push it. And let's say the easiest thing is you just imagine, instead of only doing single and 2 qubit gates, you could do multi-qubit gates. Or as you might know, that these superconducting qubits, they have more than just 2 levels. So there's 0 and 1, but then there's also the higher excited states. So you could also think about taking them into account. For this, you wouldn't even need to touch the processor itself. But then the next step would be, for example, to optimize really the physical connection and positions of the qubit. But you can go even one step beyond, and this is what we call digital analog approach then of quantum computing. So you could also place different physical elements on the chip. For example, in the superconducting chip, what you have is open transmission lines to connect different parts of the chip. And these are a continuous of mode. And you could actually use this physics, which is behind these bosonic modes, for example, to emulate in quantum chemistry applications or so. So there are different levels of co-design, and you can go just from the algorithmic part, but all the way down to really changing the hardware and the toolbox that you have in the hardware.
Interesting. Part of the reason why I was asking is because one of the biggest challenges in semiconductors, in the semiconducting industry, is actually, well, at a much larger scale, of course, is the design of the chips. So this is something that we have been thinking quite a lot internally, how or when we are going to meet a similar, when we are going to meet similar problems in the quantum computing industry, where designing the chip is actually going to become a challenge in itself, because you have so many elements that you want to put on the physical chip. And optimizing over that is usually incredibly hard. Interesting problems. Yeah, maybe if Andre, I know you're always
go ahead.
Slapping my wrist because I ask or speak too much. But I have another question, Jan, if you don't mind.
Yeah, sure. Go ahead.
Thanks. What are your views on scalability? Since I kind of mentioned scalability just now. I mean, it could be a very general answer, right? It doesn't have to be specific to IQM. What are your views on scalability for superconducting chips? Do you see things improving? Do you think we are going to have, and I just pick a random number, let's say 1,000 qubits within 5 years? And is it going to be on a single physical chip, or are we going to have weird designs where smaller chips are somehow connected? What are your views on that?
Yeah, so about the number, at least it doesn't sound impossible, 1,000 qubits in 5 years. I'm not promising anything, but at least the number seems possible. So my view is, if you look a little bit on the history of how the field evolved, it's typically, it was pushed out of smaller university research labs, and they have their fabrication facilities and PhD students going in and going out. And I think what we will see is, as the technology is now emerging and going more towards real industrial production, let's say, we will see breakthroughs in realizing the processors. And I think there's still a lot of potential that can be raised just by using more professional fabrication foundries infrastructure. And I think with these technologies, the 1,000 qubits can be reached. If we are then using the same technology also to go towards the million, I'm not so sure. And I think then we need technologies that you mentioned, like putting different parts of the processor on different parts of chips, or for example. This is something that we already see now, that people are using this flip chip technology, for example. And then part of the, for example, of the readout chain is on the other side of the chip. And I think we will see more in this direction. And I think we will see much more professional solutions in the future that help scaling up the systems.
Well, thank you so much for all these details. There seems to be more than one way to achieve supremacy or advantage, and certainly a very short and near path to at least practical quantum computing. I believe, Jan, your approach of co-design from the strategic business side not only includes clients and partners, but also universities and education with that. as well as general outreach and recreational aspects on how to make this accessible and fun, which is something that we talk a lot about here with Tommaso and Denise. So excited to see where this leads us. Thank you for being our guest. I hope you all enjoyed Season 1, Episode 3 of the Worldwide Quantum Week Detangled. You have been detangled. Have a great day.
Yeah. Thank you, everyone.
Thank you.
Thank
Bye,
you.
everyone.
Have a good day. Bye.
Bye.
Bye.